The second half of 8.7 has to do with the bottom of the card here. So this is on the yellow card. We're going to be looking at Taylor polynomials and Maclaurin polynomials. So Maclaurin polynomial is just a special case of a Taylor polynomial. So this is the type of stuff we'll be working with for the second half of Chapter 8, in addition to what's called a power series. So we're still going to be using our convergence and divergence tests. Typically, second half of Chapter 8 will involve the ratio test and the geometric. Occasionally a couple other tests, but most of the time these are the two tests that we will be working with. So we still need to know our convergence tests, so make sure you have those down. So for 8.7, the part that we're going to be working with is what's called the definition of the nth Taylor polynomial and the nth Maclaurin polynomial. So if f has n derivatives at c, so c is what we call our center, then the polynomial given by this definition right here, so this is finite. So this is our function evaluated at our center c, and then we take our first derivative, evaluate it at the center c, and then we multiply that by x minus c. And then we add to that the second derivative evaluated at c divided by 2 factorial times x minus c quantity squared. And we keep repeating that until we have enough terms, and they'll tell us, find the, 5th degree Taylor polynomial or 4th degree Taylor polynomial, meaning we'll take out 4 derivatives and then evaluate that derivative by whatever our center is. If our center is 0, okay, if our center is 0, then that's just called the Maclaurin polynomial. So Taylor polynomial is our generic phrase where our center can be whatever, and then if it's specific at 0, then we call that our Maclaurin polynomial. And so how we talk about that is we say the polynomial is said to be expanded about c or centered about c. And so one thing to kind of watch for is our derivative. So like whatever derivative that we're working with should always match to our degree. Meaning if we're working with the third or the second derivative, it would be the second 2 factorial and the power of 2. So second derivative, 2 factorial, power of 2. So if we're working with our third degree, then this would be the third derivative divided by 3 factorial to the power of 3. And so we'll be using this often, whether it's in our polynomials or our power series, so that's something to kind of make sure that you're always paying attention to. So let's go ahead and take a look at an example here. Okay, so wait, let me hit this again one more time. So our Maclaurin polynomial is when we're centered at 0. I need to make sure I say that again. Okay, so again, Maclaurin polynomial is when we are centered at c equals 0. So just to get an idea of what we're trying to do, just as a quick little overview, is we're trying to figure out how to turn our graph. So I'm just going to do one period of the sine graph. So if this is f of x is equal to sine of x, I'm trying to find a polynomial expression that would represent the sine of x. So I'm trying to figure out, what would give me a function that's a polynomial that would look kind of like this graph here. And so what we start with is we say, okay, I'm going to figure out where I want to be centered, meaning what point do I want to start at. So let's say I start right here at pi. I could start wherever, but let's just say I start at pi. And I want to create a polynomial that looks like sine of x. And so first I would say, okay, well, if I have this line right here that looks like sine of x as long as I'm near pi. And then what if I take a parabola and say, okay, well, that line's not a good approximation unless I'm blam right there. So what if I take a quadratic? So what if I take, a quadratic, which, okay, maybe that will look good just between pi and 2 pi. So there's a pretty decent approximation. And then I could say, okay, what if I take a cubic? So what if I take a cubic graph? And then now I have a pretty good approximation, and then so on and so forth. So what we're really just trying to create is near the center, wherever we are, we want to have a good polynomial approximation to the section around where we're centered. And so it will be closest as long as we're near where we're centered, and we create, you know, this cubic graph that looks kind of like our sine of x graph. So if I go beyond that, of course, it's going to be a terrible approximation because we know the sine of x doesn't keep going up. It would bend and curl back down. Okay? So that's just an overview of what we're trying to do. Okay, so the directions say to find the nth Taylor polynomial centered at C for my function, the square root of x. And I want this to be out to the 4th degree, so that's what this means. So we will go to the 4th degree, meaning we will need 4 derivatives. And then we're centered at 1. And then when we have that creation, we want to use that to approximate what is the square root of 1/2, right? Because if f of x is the square root of x, we want to approximate what is the square root of 1/2 using our Taylor polynomial formula. So our first step is we want to find 4 derivatives. So that's going to be our first step. So f of x is the square root of x, so that would be x to the 1/2 power. And so from here, I just want to find 4 derivatives. And one more. So I found the 4 derivatives, and now what I have to do is I have to evaluate each of these derivatives at c equals 1. And so we're evaluating at c equals 1 because that's our center. So I'm going to scoot down here real quick. So what we're trying to find are these coefficients here. What is f of c, f prime of c, f the second derivative of c, and so on to the 4th. So when I replace x with 1 and I take the square root of 1, I'm just going to get 1 back. So same thing here, regardless of my power on x, as long as my value for x is 1, this portion is going to be 1. So if I do 1 times 1/2, that will just give me 1/2. So I can see all the way down, because x is equal to 1, that the coefficient here is what is going to be my value. Because when I replace x with 1, it's just going to be 1 times 1/2, 1 times -1/4, 1 times 3/8, 1 times -15/16. So each of these values are just going to be those coefficients. And so now my third step is just I'm going to follow the pattern of the Taylor polynomial and expand to the fourth degree. So I know that my function is the square root of x, and I want to approximate that function with the fourth degree Taylor polynomial, so like that. Okay, so this is my function, and I'm approximating it, meaning I'm rewriting the square root of x as a polynomial, and I'm going to expand it till I go to the fourth degree. Okay. All right. So this part is just to clarify what we're trying to do. All right, so here's the fourth degree Taylor polynomial. So I'm going to kind of scoot this down here real quick. So, or let me zoom out a little bit. Okay. Okay, so this is what I'm going to be referring to when I look up here. So it starts out with f of c. So my f of c is equal to 1. So f of c equals 1. Okay, so let me slide this up. So this is 1, and now plus f prime of c, which is 1/2, times x minus c to the power of 1. Okay, and then plus the second derivative, which is negative 1/4 over 2 factorial times x minus c to the power of 2. Okay, I'm going to slide back down here so you can see what I'm doing. So do you see this? So I'm finding the second derivative evaluated at c, which was down here, negative 1/4, right? Negative 1/4. And then I divide it by 2 factorial, and then I'm going to multiply by x minus c squared. And then I'm going to keep doing that, right? So it'll be the third derivative over 3 factorial x minus c cubed. So here's my third derivative, which is 3/8. Third derivative, so over 3 factorial times x minus c cubed. And then one more here. So then this is going to be plus my fourth derivative, so over 4 factorial times x minus c to the power of 4. Okay. And then now I'm just going to simplify this a little bit so I don't have these over 4 factorials. So 2 factorial is the same as 2. So this will be negative 1/4 divided by 2. So negative 1/8. 3 factorial is the same as 6, right? 3 times 2 times 1. So this will be plus 3 over 8 times 6. And then 4 factorial is 4 times 3 times 2 times 1, so that would be 24. And then I'm going to go ahead and reduce this just a little bit so I can, let's see, so that would be divide by 3, divide by 3. So negative 15 divided by 3, so that would be negative 5. And then this would be 24 divided by 3, which is 8, and 16 times 8 is 128. And this reduces as well, so I'm going to back this up. So 3 over 48 is the same as 1 over 16. Okay, so there is my fourth degree Taylor polynomial to approximate the square root of x. And so now I'm going to do the second part of the directions, which is said to approximate the square root of 1/2, right? Let x equal 1/2. So f of 1/2, which equals the square root of 1/2, will be approximated by whatever this value is when I substitute in 1/2. So I'm going to replace all my x values with 1/2. and then simplify that. So each of these 1/2 minus 1 is just going to be negative 1/2. So negative 1/2 times 1/2. And then negative 1/2 squared. And then this is negative 1/2 cubed. And then negative 1/2 to the 4th. Okay. So now we can add and subtract and do all of this by hand, but I'm not going to. Okay, so I'm just going to give you a decimal approximation to this. So this is 0.7085. So we could add and subtract this and get a fraction answer for this. And we know that the square root of 1/2 is the same as root 2 over 2, which we know is 0.707 if we try to use our calculator. So if I use my calculator to approximate the square root of 1/2, I would get 0.707. If I did this, I could find a fractional equivalent, but I just did this as a decimal, so I got 0.7085. So that means we could evaluate square roots without having to use calculators. It's a little bit tedious, right? And calculators and the convenience of it is pretty nice. And then one other thing I want to make sure that I state with this example, because I know I said it, but I want to make sure that we understand this, that if I were to graph the square root of x, I'm going to go ahead and do that. So there's the square root of x, and then if I were to type in this function here, so I'm going to just type in the first two terms, so 1 plus 0.5 times x minus 1. So centered, I'm centered at 1, and so I'm going to look to see what does the first two terms, what does that look like compared to the square root of x. So there's the square root of x, and here's my first two terms. So that's the linear approximation, and I'm centered at 1, so near 1, and so that's not a very good approximation. So what if I add one more term here? So I'm going to go back to my y equals and add in this term. And then graph it again. And so now does adding one more term make it a little bit better? And so if I look here, there's the parabola approximating the square root function, which looks pretty good to me. I'm going to change my window just a little bit because I don't need to be quite as wide out. And so that is a very good approximation. And if I add one more term, so if I add in the 13th degree, or the 13th degree, the third degree, so plus 1 divided by 16, and then x minus 1 to the third, and then graph that. And so every time I add a term to my polynomial, my approximation gets better and better, right? And further out. So it's expanding, you know, how good my approximation is every time I add a term, and it's making it look, you know, more and more like my square root function, okay? So, I don't know, I think that's pretty cool, okay? All right, last little bit here. Or, you know what, that's it for today. Let's, so we'll just do the first 8.7 example, and then the second one we'll save and do on the block day.